Good day, everyone. This time we're going to discuss integration and some applications. It will be on Part 2D to Part 2E. So earlier, we already had discussed the indefinite integral, and the definite integral wherein we have your introduction to the definite integral, the mean value theorem for integration, and the fundamental theorem of calculus. So this time we're going to discuss part 2D, which is on area of a plane region and the arc length of a plane curve. The integral sign, which looks like an elongated S, is interpreted as the sum of the area under the given curve. That is, the most common interpretation of the integral is in terms of the area under the graph of the function. So if you take a look at this one, if you have a function y is equal to f of x, you will weight it here from a to b, then this one, which is the graph under this curve, is actually interpreted as the integral of y, which is your f of x, dx from a to b. So we can try to compute this area by approximating the region with many thin rectangles. So like this, we have here a is equal to x of 0, then we have x of 1, x of 2, up to certain value x of 6, which is your b, if you have the interval from a to b on the x-axis, this is your function. Notice that for the first rectangle here, we have here the base is x of 0, x of 1, and its height is f of c sub 1. Sun is f of c sub 1. So that the area of the first rectangle, this first rectangle, is the product of its height and width. So what is its height? We have here f of c sub 1 times this, we call this your delta of x. Delta of x sub 1. Call this delta of x sub 1. For the second rectangle, the base of the second rectangle is the interval, if you take a look here, x of 1 to x of 2. So while its height is f of c sub 2. So meaning to say, the area of the second rectangle this time is the product of its height, which is equal to f of c sub 2 times delta of x sub 2. And so on, up to this one, we can have, if we represent this as your x of 5, and this is supposed to be your x of 6, then you will have your, this one is actually the area again of this one is f of c sub 6 times delta of x sub 6. So that's what I was telling you earlier. You have that one. So the nth rectangle, the base of the nth rectangle is this interval, x sub n minus 1 to x sub n, while its height is f of c sub n. If we continue this up to your x sub n. So the area of the nth rectangle is a product of its height and width, that is f of c sub n. We have c sub n there, and we have your delta of x sub n. So the total area of the n rectangles is now given as f of c sub 1 times delta of x sub 1, so that's your s sub n, plus f of c sub 2 delta of x sub 2, plus up to f of c sub n delta of x sub n. So you can see from here, this area here of rectangles will constitute the area under the given curve. So this one can be interpreted as the sum of f of c sub k delta sub x sub k, k equal to 1 to n from this notation, so that if we take the summation of f of c sub k delta of x sub k, okay, over all of these values, now we call this actually your Riemann sum. So again, this sum approximates the area, this area, under the given curve. Sometimes we denote it as A of R or the region R. Note that as D approaches 0, we get a good approximation of the region. Mean to say, if you try to make the norm here, that is you make as many rectangles as you can, notice that you have lesser value here, lesser value up here, so that you'll be able to approximate the area under the given curve. So that the area under the given curve is actually, if you make this as small as possible, you take the limit of the norm D approaches 0, the summation of f of c sub k delta sub x sub k. So you make your rectangle as small as possible, and it is denoted by the sum of the area under this given curve is now the integral from a to b of f of x dx. So we take the following example. You're asked to find the area of the region bounded by x equal to y squared plus 2 and y equals 4 minus x. Now, to get the idea of how the region looks like, then we have to sketch the following. Actually, this will be solved using two different ways. The first one would be using your horizontal strip, and the other one would be using your vertical strip. So let's try to sketch the function x equal to y squared plus 2. And to say, what do? We have to solve some values. So from y squared plus 2 is equal to x, you can solve for y. Y is equal to minus plus square root of x minus 2. You can transpose 2 here, so you have x minus 2. But this is y squared, so that's equal to y equals minus plus square root of x minus 2. Computing for the values, notice here that x should be greater than or equal to 2. Otherwise, it will be a complex value. We cannot solve that one here. So when x is equal to 2, so because we start with 2, you will have y is equal to 0. When x is equal to 3, you will have x. So you have 3 minus 2 square root will give you this one. There's a minus and plus there. So you have minus and plus 1. When x equal to 4, you will have this value. And you can actually try to verify all of these values later. Then, we need also to sketch the other one, which is y equals 4 minus x. And to do that, we have to again give some values for x and solve for y. So when x equal to 1, you will have 4 minus 1, that will give you 3. When x is equal to 2, that will be 4 minus 2, so you will have 2. And down the line. So what did you notice? This one is actually a parabola which opens, because this is positive here, parabola which opens to the right. And this one is actually, or this, is a line which slants, because the slope is negative, slants downward to the right. We also need to compute for the points of intersection of these two graphs, so that we will be able to indicate the area of the region. So that you now have the points of intersection. When you equate this, x equal to y squared plus 2, and the other one is x equals 4 minus y. That should give us y squared plus 2 equals 4 minus y. And that means to say, you can rewrite this as y squared plus y plus 2. We have y squared plus y supposed there, then plus 2, then minus 4 equal to 0. Solving further, we have the following. That is y squared plus y minus 2, plus this is minus 2, is equal to 0. Now we try to solve for y. Factor it, and we will have y minus 1 and you have times y plus 2 is equal to 0, meaning to say y equals 1 and y equals minus 2. So when we substitute y equal to 1 and y equal to negative 2 to x equals 4 minus y here, so when y is equal to 1, you will have 4 minus 1 there, so x will now become 3. And when you have negative 2 for y, that's 4 minus a minus 2, x is equal to 6. So the point of intersection will now be x is 3, y is 1, so you have this, x is 6, and y is negative 2. So we have 2 points of intersection. So let us take a look at the sketch. Here we have the value so that we can sketch for the parabola which opens to the right. Okay, this one, if you take a look, this is the parabola which opens to the right. That is when x is equal to 2, y is 0. Here, this one, x equal to 2, y is 0. When x is equal to 3, y is plus or minus 1. So this is 3. So you have there, y is positive 1 because it's positive 2. So it's positive 1. And y is equal to also negative 1. And when x is equal to, let's just take a look at 6. When x is equal to 6, y is equal to positive 2 and y is equal to negative 2. On the other hand, the other graph, this line here, is from this one. That is, we have some values that we computed earlier. When x is equal to 1, y is equal to 3. When x is equal to 1 here, y should be equal to 3. When x is equal to 2, y is equal to 2 also. So you have that. When x is equal to 3, y is equal to 1. And down the line, that is when x is equal to 6, y is equal to negative 2. As for these points of intersection, that was also computed earlier, which is at 3, 1. So x is equal to 3, and y is equal to 1. And at 6, negative 2 is 1. 6, negative 2. So those are the graphs of y squared equals x minus 1 and y is equal to 4 minus x. What does it mean? It means that we're going to solve for this region. Okay, this region. Because it's bounded by these two graphs and you have to. And we make use now of our integral, the definite integral. So for the first solution there, we try to make use of our rectangular strip which is horizontal. So meaning to say, this one here is dy. This one, it moves on the y-axis, so we have here a dy. We're going to evaluate it from a value wherein our limits of integration is on y. So let us take a look at the x right curve. We need to say this curve, as we move from here to here, that could be, this curve is actually equal to, in terms of, you have 4 minus x, now y is equal to 4 minus x. So, meaning to say that that right curve there is y equals 4 minus x. It's 4 minus x, or in other words, that x is equal to 4 minus y. So we express our x in terms of y because we have here dy. So express your right curve, the curve on the right, to be your 4 minus. And then, as for the left curve, this one, we have x sub l equals y squared plus 2. This one, it's already expressed in terms of y. Remember, we're in dy there. So we can make use of that one. So again, the area of the horizontal strip, and to say if we get this rectangle here, come up now with length times width, which is our x sub r minus x sub l, this one, x sub this one. This is your x sub r, this is the right part, from the right, going to the minus x sub r. So x sub r minus x sub l is the left. I'm sorry. You have right to left. And then you have dy. Okay, that's your width. So dy. So meaning to say you have the area of the region R. Now this, so for a specific rectangle, you have this. If you take the summation of all of this rectangle, you come with this. The integral from, you evaluate it from y equals -2 to y equals, notice that y here is equal to 1. So from -2 to 1, and then you have x sub r. So on the value here, which is equal to, what's our x sub r? Again, we computed that earlier. That is x sub r equals 4 minus y. So it should be in terms of x, in terms of y. No? And left curve is y squared plus 2. So in terms of y, but you have a dy there. So you now have 4 minus y minus x sub l is y squared plus 2 dy from -2 to 1. So y here from -2 to 1. You know how to integrate this. Okay. Simplify that one first, which will give you, you have minus y squared, then we have minus y, then 4 minus 2 will give us plus 2. So we have dy. From -2 to 1, meaning to say, again, how do we solve for this one? This is negative y to the third all over 3. This is minus y to the second all over 2. Then we have 2y. Evaluated from -2 to 1. When you substitute those values, we'll have 1/3. Since we have this one, the upper limit is 1 times 1 to the third minus 1/2 times 1 to the second power. Then 2 times 1. Then minus, again, -1/3, -2 to the third power there. So -1/2 minus 2, because we have minus 2, then to the second power, plus 2 times minus 2. That's algebra now. All you have to do is compute. The value now is 9/2 square units. Okay, 9/2 square units, this one. The area under this curve is 9/2 square units. Now, what happens if we make use of the area of a vertical strip? So, we're going to solve from here. So, you will now have your dx instead of dy. Here, for solution 2, notice that if we make use of your dx, we have to consider two regions. For the region 1, because if you take a look at this one, here the upper curve is this. Whereas on this part, the upper curve is this line. So we cannot make use of just one region to compute. You have to consider two regions to compute, making use of your vertical strip. So let us take a look for the first region. What will be your upper curve? The upper curve will be this one, which is, it should be in terms of this value. Y sub u is now equal to the square root of x minus 2. Because you will have dx, so it should be in terms of x there. Then you have lower curve will give us in this region is actually equal to what value this time? We will have this, the negative of squared. This one, this is the negative of square root of x minus 2. Because we have here plus or minus square root of x minus 2. So the upper is positive square root of x minus 2. The lower is the negative of square root of x minus 2. As for the second region here, notice that we have here the upper curve is equal to, you have 4 minus x, this one, in terms of x, so it's 4 minus x. And the lower curve is this one, which is equal to the negative square root of x minus 2. So the solution wherein we make use of the vertical strip is actually longer, but is still should have the same answer. So let's take a look at the answer there. So again, you have your upper curve, your lower curve. For reference, we have the area of a vertical strip. If you remember, is y sub u minus y sub l times, this time you have length times width. So our length this time is y sub u minus y sub l. Then we have our dx as your width. So if you recall, our y sub u, which is the upper curve, is positive square root of x minus 2, and our lower curve is the negative square root of x minus 2. Then because we have here your dx, then that's dx. But when you compute for this, it's simply twice of the square root of x minus 2 dx. So for area of region 1, how do we know these limits of integration? Again, we have to compute for the points of intersection. So if you take a look at the value, let us there, then you will have from 2 to 3 of 2 square root of x minus 2 dx. Okay? And then we have here, when you compute, that will give you, if you take a look, you have x minus 2 dx. So you can replace your u to be, or you can replace x minus 2 with u, and then compute for du, which will give you dx, so the derivative of u there, the derivative of x, and that's a constant, so that's 0. Now, since we use substitution, then we have to consider when x is equal to 2. So when x is equal to 2, what will happen to our u? You will have 0 for your u. And when x is equal to this one, 3, what happens to u? You will have u will be 3 minus 2, so you will have value equal to 1. So we are now ready for substitution. We come up with the following. That is, instead of 2 to 3, 2 square root of x minus 2 dx, that becomes from u now, when x equal to 2, that becomes u is 0. When x equal to 3, we will have u is equal to 1. Then 2, this one is replaced by u to the 1/2 du. But from our integral formulas, we now have, if this is our n, that's 1/2 plus 1 will give us, how many? 1/2 plus 1 will give you 1/2 plus 2 over 2. So we'll have 3 over 2. All over, you have 3 over 2. But since we have 2 times, when you have 3 over 2, you should have 2 over 3. So 4 times all over 3. Evaluated now from 0 to 1. And that should give us the value for third square root units. Or 4 over 3 square units. But that's not yet the answer because it's just region 1. So for region 2, we have the following. Again, this should be your upper curve and your lower curve. Area of the vertical strip will now be, you have y sub upper curve minus y sub lower curve times our dx. So that, since y upper curve is 4 minus x, that's 1, and our lower curve is minus square root of x minus 2, and you have your dx there. So computing for the vertical strip, we have the following. 4 minus x, then this is minus of minus, so that becomes plus square root of 2 minus x. And if we take all the summation of these vertical strips, then we'll have integral of 4 minus x plus square root of x minus 2 dx, evaluated from 3 to 6. You can rewrite this as the integral of 4 minus x dx from 3 to 6, integral of, because this is sum, no? Square root of x minus 2 dx evaluated from 3 to 6. So that if we let u be equal to 4 minus x here, then our du will simply be dx. Now you can compute for that. When x is equal to 3, what will be the value of u? X equal to 3, you will have u equals 1, 4 minus 3, diba? Then when x is equal to 6, because we have 6 here, the value of u will now be equal to 4. We have 4. This one, 6 minus 2 will give you 4. So we now have the area of the region of the integral from 3 to 6 of 4 minus x dx plus 3 to 6 of square root of x minus 2 dx will now be equal to, we have 4 minus x dx evaluated from 1 to 4, okay, u to the 1 half. Because our u is equal to x minus 2. So x minus 2 square root, so we have 1 half. Solving for this, you will have, when you evaluate, that becomes 4x minus 1 half x squared over 2. I'm sorry, 1 half minus 1 half x squared. Okay, that's already x squared over 2. Then you have from 3 to 6 here. But because we substituted this value with u, should also change the limits of integration, which is from 1 to 4 there. So 2/3, because that's u to the 1 half, that will be u to the 1 half plus 1 all over 1 half plus 1 will give you this. 2/3 u to the 3 over 2 evaluated from 1 to 4. Simplifying further, you try to solve for the value, you'll have 19 over 6 square units. So that when you add these two, okay, you have this one, 4 over 3rd plus 19 over 6 equals 27 over 6. So what is 27 over 6? It's 9 over 2 square units. Same answer as we had on our first solution. Again, we have to consider this time, because we just considered your two regions, because we made use of your vertical strips. Okay? Now for the arc length of a plane curve, we have the following. If we have f be a continuous function on AB, and suppose also that the derivative f of x is continuous on AB, then the length of the curve y is equal to f of x from x equal to a to x equal to b is given by the following formula. That is the integral from a to b of the square root of 1 plus f prime of x squared. And to say you square the derivative of the function and then add it with 1, then put it under the square root and take the x. Okay, so that's our L. So that is, if we use the Leibniz notation for derivative, we have the following. The integral of a to b, the square root of 1 plus dy dx squared dx. That would be the length this time of a plane curve. So for the interpretation, we actually have the following. This is your, say, your curve. And we just would like to take this part, the length of this. That is, we take the value dl equals square root of 1 plus f prime of x squared dx. So we now have this one. Be sure dy, then you have your dx there. So dl, that's the length of this curve. Okay. So L here is actually the function. Just take this value and simplify it to be this line here, which is our derivative of L, derivative of this line. So find the length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. We can simply make use of our formula. So for the top half of the curve, we have the following. Y squared equals x cubed. Okay. So y squared equal to x cubed. That means to say, if we take the, if you divide 2 here by 2, the exponent here by 2, divide the exponent here by 2 again. I mean to say, we raise it to the 1 half. Then you will have y is equal to x to the 3 over 2. Okay. But dy dx, the derivative of y, that's easy to take its derivative already, is an exponent, so you will have 3 over 2x to the 1 half. Now recall our formula earlier. L is equal to the integral from a to b of the square root of dy over dx squared dx. So we now have our dy dx there. Just simply plug in those values. So you have, it says from 1 to 4. X is from 1 to 4. So you have 1 to 4 because you're making use of our dx. Then square root of 1 plus, this is our dy dx, which is 3 over 2x to the 1/2 square. Simplifying that further, you will have integral from 1 to 4 of 1 plus, this will give you 3, that's 9 in the square, 2, that's 4 in the square, x to the 1/2 in the square is, that's x. And to say, we now have the following. If we try to let this value here to be equal to u, then you will have u to the 1/2. Huh? So this, our du here will give us, this one is 0, that's 9 over 4 dx. So dx now is actually equal to 4 over 9 du. If you try to simplify that one, note that when x is equal to 1, what happens? You will have 1 plus 9 over 4. That is equal to 13 over 4. But when x equal to 4, because it's 1 to 4, when x equal to 4, you will have 9 over 4 times 1 plus 9 over 4 times 4. So that should give us a value be equal to 10. Okay, so that from here, you will now have, since you have this quantity, and we replace it already by u to the 1/2 du here, and we also change the limits of integration from 1 to 4 into 13 over 4 to 10, and we have 4 over 9 integral of u to the 1/2 du evaluated from 13 over 4 to 10. Then this will give us the following. If we simplify, 4 over 9, this is u to the 1/2. So you have u 3 over 2, u raised to the 3 over 2, then this one is 2/3. That should be over 3 over 2, but when you put it here, it becomes 2/3 there. So evaluated from 13 over 4 to 10, that should be, okay, simplified as such. Have this, 4 over 9 times 2/3. You have 13 over 4 to 10. Meaning to say, it's just repeated them. But anyway, that's equal to this, 8 over 27. So, you have this answer. That is, the length of the arc of the semi-cubical parabola, y squared equal to x cubed between the points 1, 1 and 4, 8 is this value. 1 over 27, the quantity 80 square root of 10 minus 13 square root of 13 units. You can actually verify this when you try to simplify that one. And how does it look like? This is the graph here. This is what you're asked to compute. The length of the arc of this semi-cubical parabola. So from 1, 1 to 4, 8 with this function. Now for your exercises, we have two exercises here. You can try solving this one. Exercise 1, which is on the area of the shaded region, and this one, the other exercise, is on the length of the curve y equals ln cosine x from the point where x equal to 0 to x equal to 4.